Hey everyone, as you remember last time we were introduced to the chain rule. The chain rule tells us how to compute the derivative of a composite function, a function evaluated at another function. And this is what the chain rule looks like. Now we also remembered it in words, and here it is. The derivative of the outer evaluated at the inner times the derivative of the inner. That's the chain rule. And this is exactly what we have. We might label f the outer function and g of x the inner function. And so in that context, we have f prime, the derivative of the outer, evaluated at the inner, times the derivative of the inner. So to get the ball rolling, let's just do something for the sake of review. And let's say derivative of cosine of 3x to the fourth minus 5x squared. So this is cosine evaluated not at x, but cosine evaluated at a function of x. So this is definitely a composite function. Cosine is the outer function, and 3x squared plus 5x is the inner function. And the chain rule tells us what we're supposed to get. We're supposed to get the derivative of the outer. So let's write that down. The derivative of the outer evaluated at the inner times the derivative of the inner. So we have a nice template here that we can fill out. The problem's almost completely done already. Now that we have the template laid out, all we have to do is fill in the blanks. So first of all, the derivative of the outer function. The outer function is cosine evaluated at something. This is the outer function, cosine evaluated at something. So the derivative of the outer is negative sine evaluated at something. So here's the derivative of the outer, negative sine evaluated at something. And we evaluate this at the inner function, 3x to the fourth plus, minus 5x squared. So, yep, I should have left it alone. Oh well. 3x to the fourth minus 5x squared. There we go. The derivative of the outer evaluated at the inner times the derivative of the inner function. That's the derivative of 3x to the fourth minus 5x squared. So that's 12x cubed minus 10x. And bingo, we have it. So that's a little bit of a review. We also did something else last time. We extended the result to the composition of 3 functions and even 4 functions. Let's take a look at that. Remember what we do in a situation like this where we have the composition of 3 functions. We have f evaluated at g, evaluated at h of x. And remember what the key is. We always start at the outermost function. So we identify the outermost function, and that's f. And we compute the derivative of the outermost function, evaluated at everything inside. So here's the derivative of the outermost function, and we evaluate it at everything inside. G evaluated at h of x. Then we move in one layer to the next outermost function, which is g. And we compute the derivative of the next outermost function evaluated at everything inside of it. So the derivative of the next outermost function, g prime, evaluated at everything inside of it, h of x. Are we done? We keep on going till we get to the innermost function, and then we multiply by the derivative of the innermost function. So we did a few of these exercises last time. Let's do another. Here we do have the composition of three functions: cosine, evaluated at sine, evaluated at 10x squared. And we remember the place to start is at the outermost function. So we identify cosine as being the outermost function. And we compute the derivative of the outermost function evaluated at everything inside. Now, what's the derivative of cosine evaluated at something? If you say negative sine evaluated at something, then you're right. So the derivative of the outermost function is negative sine evaluated at something. And we take the derivative of the outermost function and evaluate it at everything inside of it. Sine evaluated at 10x squared. Are we done yet? No, not by a long shot. Now what we do is we move to the next outermost function. Sine evaluated at something. We compute the derivative of the next outermost function, evaluated at everything inside of it. What's the derivative of sine evaluated at something? Isn't it cosine evaluated at something? So here's the derivative of sine evaluated at something. And we take the derivative of sine evaluated at something and evaluate it at everything inside, 10x squared. Now are we done? No. We have to keep going until we get to the innermost function and we compute the derivative of that. So we're at the innermost function now. We multiply by the derivative of this thing, 20x squared. Voila, there we have it. Now I guess technically I could move this out front. This answer's fine. Usually if we have the product of polynomials and trig functions, we like to put the polynomial out front. So if we were rewriting this and making it look a little nicer, I guess whoops, shame on you people. How come nobody said anything to me? Derivative of the inner function 10x squared is 20x. Okay. Don't be bashful, you won't hurt my feelings. Derivative of the innermost function is 20x. And now I'm just going to tidy this up. Bring the 20x out front times sine of 10x squared times cosine of 10x squared. And voila. No? Boy, maybe I need glasses. So you bring the 20x out front, negative 20x times sine evaluated at sine of 10x squared there we go, sine 10x squared times cosine of 10x squared. Okay, beautiful. So after 3 attempts, we finally have it looking nice. Now we're going to get into something that we haven't done before, but it's something that we're going to see all the time, and we need to know how to deal with it. Okay, this is the special scenario that I was referring to. F of x is defined as x to a power. And f of x is going to be our outer function. G of x, the inner function, can be anything. As a matter of fact, g of x can be the proverbial ham sandwich that we've talked about. Now, according to the chain rule, if we compute the derivative of f evaluated at g of x, that we have the derivative of the outer, f prime, evaluated at the inner, g of x, times g prime of x. And the question is, how does all of this play out when the outer function is something raised to the n power? So let's analyze this. So the derivative of f of x is the same as the derivative of x to the n. And that's just the power rule. N times x to the n minus 1. Now, in the context of this exercise, f evaluated at something is the outer function. So let's note that. The outer function is f evaluated at something. Well, this is our model for f of x, or our definition for f of x. F evaluated at x is x to the n power. So what is f evaluated at something? Well, this something plays the role down here that x plays up here in our model of f of x. So every place we see an x up here, we put something down here. This is our outer function, something raised to the n power. Now what about the derivative of the outer function? Well, we just reminded ourselves that the derivative of f of x is nx to the n minus 1. So the derivative of f evaluated at something is going to be n something to the n minus 1. It's going to look like this. And you know what? Maybe I'll insert f prime of something here. F prime of something equals n something to the n minus 1. This is the derivative of the outer function. So the derivative of the outer function, f prime of something, is the same as n something to the n minus 1. This is the derivative of the outer function. And then we have to evaluate it at the inner function, g of x. So we have the derivative of the outer, n something to the n minus 1, evaluated at the inner, times the derivative of the inner. So let's see, times derivative of the inner, which is just g prime of x. This is how, tell you what, let me not summarize my case yet. I have more evidence to present to the court. F evaluated at g of x. What is that? Well, here g of x plays the role that x plays up here in our model. So every place up here in our model that we see in x, we're going to put g of x down here. So f evaluated at g of x, that's the same as g of x to the n power. This is f evaluated at g of x. And we just saw what that turns out to be. It turns out to be this thing. N something to the n minus 1. So here's the derivative of the outer. The outer function is the raising of something to the nth power. So here's the outer. G of x is the inner. So we should get the derivative of the outer function, n something to the n minus 1, evaluated at the inner, g of x. Okay. And then the chain rule says we multiply by the derivative of the inner. Which is g prime of x. This is important for a few reasons. One, it's the derivative of a function raised to a power, and we're going to see that all the time. We're going to see it all the time, trust me. The only way that we're not going to see this all the time is if we quit calculus right never and take another, if we quit calculus right now and never take another math class, okay, then we won't see it. But if we continue in calculus and we continue in math, we're going to see the derivative of a function raised to a power all the time. So we need to know how to deal with it. The other reason that this is important is that even though this is the chain rule where the outer function is raising of something to a power, the appearance of this derivative is different from the appearance of every other function to which we apply the chain rule. The appearance of this is different, and so we make it a special case for two reasons. One, because the appearance does differ so much from the chain rule that we've been accustomed to seeing. And two, since it is so different, and since we're going to see it all of the time, we need to know how to deal with it. So now we will summarize our case. Okay, here, excuse me. Here I summarize my case. That we have the special case of the chain rule, the derivative of a function raised to a power. And here's what the derivative of a function raised to a power looks like. Some function g of x raised to the nth power. And notice this, the raising of g of x to the nth power, the raising of something to the nth power, this is the outer function. G of x is the inner function. So the outer function is something raised to the nth power. That's the outer function. To compute the derivative of this mess, we need the derivative of the outer function. Well, the outer function is something raised to the nth power. So the derivative of the outer function, using the power rule, is n something to the n minus 1. There's the derivative of the outer function. And the chain rule tells us we have to evaluate this at the inner. So we take the inner function, g of x, and we plug it in to the derivative of the outer function. So there we have it. Derivative of the outer, n something to the n minus 1, evaluated at the inner, g of x. But we're not done yet. Now we have to multiply by the derivative of the inner. The inner is g of x, so the derivative of the inner is g prime of x. This is the derivative of a function raised to a power. And we've diagrammed this in the context of the outer function being the raising of something to the nth power. And we should always think of the derivative of a function raised to a power this way. And at the expense of playing devil's advocate, I'm going to say that we should always think of the derivative of a function raised to a power in another way. We look at it this way just to make sure that we really understand what's going on. But for the sake of computation, we also look at it another way. And probably if I didn't tell you this, you would adopt this way of thinking in a short period of time anyway. So I'm going to say, alternatively, we have something raised to a power here. And the first part of the derivative is n g of x to the n minus 1. I'll write that down. And if we never knew the chain rule and we were trying to compute the derivative of g of x raised to the n power, this would probably be how we do it. If nobody told us that there was such a thing as a chain rule and they never told us how to compute the derivative of a composite function, we'd probably look at something like this and say, oh, the derivative of g of x raised to the n power is n g of x to the n minus 1. It's the power rule. Of course, the power rule really only tells us how to compute the derivative of x to a power. But this looks like the power rule applied to the function g of x. So that's how I'm going to analyze this. I'm going to look at this and I'm going to say, you know what? This is the power rule as usual. And then I have to be careful because now I've just remembered that the power rule tells us how to compute the derivative of x raised to a power. And I don't know if that really works for a function g of x raised to a power. But in my mind, this is the power rule as usual. But since we're not computing the derivative of x raised to a power, but instead we're computing the derivative of a function, g of x raised to a power, the power rule doesn't work per se. We have to add this corrective factor. And that corrective factor is g prime of x. And so I'm just going to say here, derivative of the inner function. Now, when we use the power rule to compute the derivative of a function raised to a power, inevitably, this is how we're going to think of it. So fine. Think of it this way. We just don't want to lose sight of what's happening theoretically because later on, when we do integration involving, let's see, what do we call these? Composite functions. We're going to need to remember exactly what the derivative of a function raised to a power really is. So I'm saying when we do computation, we're going to be thinking this. We're going to be thinking, aha, power rule as usual. Oops, but since this is a function raised to a power, we have to multiply by the derivative of the inner function. And there's nothing wrong with thinking of it this way. When we do computations, when we compute the derivative of a function raised to a power, this is what we're going to be thinking. Oh, power rule as usual. Oh, but this is a function raised to a power. Chain rule says we have to multiply by the derivative of the inner. This is how we're going to think. Everybody who does calculus thinks this way because to a certain extent our brains are all hardwired the same way. So we're going to look at this and say, oh, okay, power rule as usual, n g of x to the n minus 1. And then we're going to stop and say, you know what, this is an x raised to a power. This is a function raised to a power. So we have to compensate. The chain rule says we have to take this and multiply it by the derivative of the inner function. That's how everybody views it, and that's fine. Just as long as we don't lose sight of this, it's going to be important to have this understanding of what we're doing when we compute the derivative of a function raised to a power. So we don't want to lose sight of this. So how should we think of the derivative of a function raised to a power? we really want to think of it both ways. When we're doing strictly computation, we're going to do it this way and we're going to think this way. And there's nothing wrong with that. This is the way every single person on earth who does calculus does the computation and thinks about the computation. But we want to make sure that unlike some people who do calculus, we want to make sure that we do not forget what's really going on here. And by the end of this course, we will be doing something called integrals and integration. And it's going to be very important to have this concept when we do that. So a derivative of a function raised to a power, we want to look at it both ways. We want to remember this both ways. And when we're doing computation, yeah, this is the way we're going to do it. This is the way we're going to think. This is a great example to start off with. Probably we want to do something that really dramatizes the chain rule. And I will say that we can do this without using the chain rule. There is a way that we can do this without using the chain rule. And the way we do this is we can simplify the inside first. We can take this thing and multiply it by itself 100 times and then compute the derivative of that. If we multiply this by itself 100 times, we're going to have a polynomial with a few hundred terms in it. Let's see, once we simplify it, I guess it'll have slightly more than 100 terms, maybe 200, I don't know. But now to multiply this by itself 100 times, it may take a couple of days, literally. And in the process, almost certainly, we're going to make mistakes. So after we spend a couple of days multiplying this by itself 100 times, we're going to have the incorrect answer, and we compute the derivative of the incorrect function. We're going to get the incorrect answer. So one way we can do this without the chain rule is to multiply this by itself 100 times and then compute the derivative of the result. We don't want to do it. And I'm not saying we're lazy, but we're not nearly as lazy as we are smart. And if there's an easy way to do something, we're going to do something the easy way. So we use the chain rule. And this is a function raised to a power. So the first thing that we're thinking is power rule as usual. Excellent. So let's see, the outer function is something raised to the 100th power. So that's 100 garbage to the 99th. Or let's see, we're just doing the power rule, aren't we? So it's 100 garbage to the 99th. So we have x cubed plus 4x squared plus 7x minus 5. Okay. Power rule as usual. 100 times this to the 99th power. And then the chain rule says we have to multiply by the derivative of the inner. (3x squared plus 8x plus 7). Beautiful. Power rule as usual times derivative of the inner. We're done. Now, just for the sake of making sure that we have the concept of the chain rule when we compute the derivative of a function raised to a power, we're going to do this again. And the raising of something to a power is the outer function. And this polynomial is the inner function. Here's the alternative way of looking at that. It's the derivative of a composite function, a function raised to a power. And the raising of x cubed plus 4x squared plus 7x minus 5 to the 100th power. The raising of something to the 100th power is the outer function. The inner function is the function that's raised to the power. So let's see what we should have here. The chain rule says we have derivative of the outer evaluated at the inner times derivative of the inner. So the outer function is something to the 100th power. What's the derivative of something raised to the 100th power? Isn't it 100 times something raised to the 99th power? That's the derivative of the outer function. And then we have to evaluate it at the inner function, this polynomial. X cubed plus 4x squared plus 7x minus 5. So we plug in the inner function, x cubed plus 4x squared plus 7x minus 5. So derivative of the outer evaluated at the inner times derivative of the inner function, 3x squared plus 8x plus 7. Bingo. We have a lot of these to do. Let's continue with some more examples. Before we do some more examples, let me just talk about notation of trig functions raised to powers. Now, we probably know this, but a reminder sure wouldn't hurt. Sine squared x, that's the same thing as the sine of x, the whole function, squared. Sine cubed of x, this notation means the sine of x, the whole thing, cubed. Sine to the k of x, the same as taking the sine of x, that whole function, and raising it to the k power. And this holds for all trig functions. Cosine squared x, that's the same as cosine of x squared. Cosine cubed x, that's the same as cosine of x cubed, and so on. Now, this notation has been in existence for centuries. I don't really like it, but it's been around for centuries. It is inextricably woven into the literature of mathematics. We are not going to get rid of it, so we might as well get to like it. No, that's not necessarily true. We're not going to get rid of it, so we might as well learn how to work with it correctly. I don't like this notation, but I've learned to deal with it. And before we go any further in chain rule exercises, I think we need to work with this and at least learn how to deal with this kind of notation. So examples are forthcoming. Okay, take a look at this. Sine to the fifth of 6x cubed minus 7x squared. We want to compute the derivative. And since we're new to working with this kind of notation in the sense that maybe we've seen this notation before, but we haven't had to compute derivatives of expressions that had this kind of notation. Since this is new to us in that sense, let me use one of my favorite words. Yep, definitely one of my favorite words. I'm going to rewrite this in notation that is a lot more difficult to misconstrue. Now this sine to the fifth means we take the sine of 6x cubed minus 7x, that whole function, and raise it to the fifth power. So I have sine of 6x cubed minus 7x squared, whole thing raised to the fifth power. This is what we're really looking at. It's the composition of three functions. And so we use the technique that we used a little bit earlier in this lecture and that we used in the previous lecture when we have more than when we have the composition of more than two functions. The first thing we do, we look for the outermost function. And in this case, we have sine of 6x cubed minus 7x squared. This whole thing is raised to the power of 5. So the outer function is the raising of something to the fifth power. That's the outermost function. So now how do we proceed? We compute the derivative of the outermost function evaluated at everything inside, right? So what's the derivative of something raised to the fifth power? 5 times something raised to the fourth power, right? So here's the derivative of the outermost function. And then it's evaluated at everything inside. Sine of 6x cubed minus 7x squared. Okay, cool. Now do you remember where we go from here? We've computed the derivative of the outermost function, evaluated at everything inside. So what do we do now? We go to the next outermost function. And that's going to be sine. We're computing the derivative of sine evaluated at 6x cubed minus 7x squared. So it's the derivative of sine, which is cosine. And I better give myself a little room here. The derivative of sine evaluated at everything inside, 6x cubed minus 7x squared. Okay. Now where do we go? Don't we keep on going until we wind up at the innermost function? So we go in again, and this time we get to the innermost function. And we multiply by the derivative of the inner. 18x squared minus 14x. And there we have our derivative. Now let's see. Can we simplify this at all? If we wanted to, let's see. This is something raised to the fourth power. And we have sine of something raised to the fourth power times cosine. So we have sines times cosines times 18x squared minus 14x. This is the only, well, this factor and the 5 out front are the only factors that are polynomials. So if we wanted to tidy this up a bit, the only thing that we could do is bring this polynomial out front and multiply it by 5. Other than that, we just have sines raised to a power times cosines raised to a power. The 6x cubed minus 7x, this is not a factor. This is an inner function. So if we wanted to tidy this up a bit, we could. We could take this and bring it out front and multiply it by 5. So that's 90x squared. 5 times 14 is 70. Okay. 70x times sine 6x cubed minus 7x squared to the fourth times cosine of 6x cubed minus 7x squared. If we wanted to simplify things, this is about as much as we could do it. On a test, I'd probably stop right here. If I'm doing homework, I'm going to simplify my answer only as much as I have to make sure that it agrees with the answer in the back of the book. Let's do another exercise. We're back. Here's another one, composition of 3 functions. Tell me, where do we start if we have the composition of 3 functions or 4 functions? Don't we look for the outermost function and compute its derivative and evaluate it at everything inside? So let's find the outermost function. Is the outermost function the raising of something to the 10th power? Let's see. What is it that we're raising to the 10th power? It's this polynomial, isn't it? But this polynomial raised to the 10th power goes inside the tangent function, doesn't it? So really, the outermost function here is tangent of something. And all of that is sort of inner. But I'll call tangent the outermost function. And we compute the derivative of the outermost function, evaluated at everything inside. So, the derivative of tangent of something is secant squared of something. So this is the derivative of the outermost function, and we have to evaluate it at everything inside. 8x to the 5th plus 3x to the 10th. So we have 8x to the 5th plus 3x to the 10th. There we go. Now what do? Don't we go to the next outermost function? Ooh, but what is it? We have tangent evaluated at something raised to the 10th. So this is the next outermost function, the raising of something to the 10th power. So the derivative of the next outermost function is 10 times something to the 9th evaluated at everything inside, 8x to the 5th plus 3x. Beautiful. And then what do? We keep on going till we hit the innermost function, right? And here it is, the inner function. So now we multiply by the derivative of the inner, 40x to the 4th, times plus 3. Now, can we simplify this at all? Well, maybe we can take this 10 and distribute it to that factor. Now, if I'm doing this on a test, I might just leave it like this. If I want to tidy it up at all, about all I can do is take this 10 and distribute it to that factor. Okay, and now I take this 10 and distribute it to that factor. 400x to the 4th plus 30. Okay. And on a test, if we wanted to leave it like this, that's fine. More examples, more examples. Okay. Cosine to the 20th sine of 3x. What do you think I ought to do here, huh? First thing, what do you think I ought to do? I'll tell you what I'm going to do, just to make sure that I get it done correctly. I'm going to rewrite this in another form. There we go. So we have derivative of cosine of sine of sine of 3x, that whole thing raised to the 20th. So cosine evaluated at sine of 3x, that whole thing raised to the 20th. This is what we have. It's the composition of several functions. And as always, we're going to start at the outermost function. And this time it is the raising of something to the 20th. This is the outermost function. So we have cosine evaluated at sine of 3x, that whole thing raised to the 20th power. It's a function raised to a power. So the derivative of the outermost function, which is the raising of something to the 20th power, is 20 times something raised to the 19th power. That's the derivative of the outermost function. And it's going to be evaluated at everything inside. Cosine of sine of 3x. Okay, we're done with that. But then we go to the next outermost function. And that's going to be cosine. And cosine is evaluated at sine of 3x. So we compute the derivative of the next outermost function, which is negative sine of something. So the derivative of the next outermost function is negative sine of something, evaluated at everything inside, sine of 3x, and then we move in again, don't we? Move into the next outermost function, which is sine. And the derivative of sine of something is cosine. Evaluated at everything inside, 3x. And then we keep on moving until we get to the innermost function. And the derivative of the innermost function is 3. Well, there are a few things that I can multiply together here. What are they? I have 3 times negative 1 times 20. So let's see, that's going to be negative 60. Cosine of sine of 3x is the 19th times sine evaluated at sine of 3x times cosine of 3x. And I guess technically those parentheses don't need to be there. So this is simplified, and this is about as simple as we can get it. Do me a favor, study this video carefully. Work the exercises along with me, and then do the homework from the text that I assign along with this. Remember, the chain rule is very important, and it continues to be important throughout calculus. So if we get it down now, we're setting ourselves up for success.